What? Oh, you don't know about. Oh boy.
Dude, that's what makes his test about it. All of his questions just straight off the.
What are we doing?
Yeah, it's like a.
It's like a okay, so there's that. There's another website that's like some teacher's personal file.
Yeah.
And he basically, they're like questions from the test banks, like the textbook provide the test bank for the teacher. And so it's the questions for the teacher to give to the students that aren't in the textbook.
But they're like,
They're not really bad, but they're just like kind of hard to see. But they get.
You guys, page 35 in your packet.
Hey, could we get, okay, so function rule to F prime. Can we talk about this? Did we get this far? No, okay. So, we talked about vertical asymptotes. We talked about that there's scores of asymptotes. We talked about how we can find the X and Y intercepts. They both end up being 0, 0. But we know that we have to go through quotient rule to get to the first derivative. So F prime G minus FG prime all over G squared. We leave the denominator alone. Don't try to pull it out. This is in the perfect place for us to look for the next things that we want to look for. So don't try to pull it out. You're just going to try to clean up the numerator. So distribute the 4x through, distribute the combine that 2x squareds together, combine like terms, and we're able to get all the way down to 36x over 9 minus x squared quantity squared.
Usually sometimes like the critical points are like very messy numbers. Like I don't know like what numbers to plug in, like at the sign line.
So if those messy numbers show up, use your calculator, right? Just find the decimal value and insert in and just get the sign. Okay, yeah, so use your calculator. But here, I think these should be pretty straightforward, right? We can choose -4, we can choose -1, we can choose 1, we can choose 4, the derivative. And to save some time, if you look at your denominator is square, which means that your denominator is always what? Really, it's just the numerator, right? The numerator is really going to decide what the sign of your value is. So, do we see any relative extrema at with our critical points?
Yes.
Where's that?
0.
That's 0, right? Yeah, there's relative minute, right? Even if there's a change in sign here, how do we know that -3 and 3 are out of the running, that we can't do anything, that there is no relative extrema at -3 and 3?
Double plus.
Right, okay, so, but let's say, even if there were a change of signs. Because they're what? Okay, they're vertical asymptotes, right? But we still place them onto our F prime sign line because they will still help separate our intervals of increase, decrease. So from here, right, we set the numerator equal to 0. We set the denominator equal to 0. The denominator gave us 3 and -3. The numerator gave us 0. And then so we tested around those points. And also those arrows kind of help us give us an idea how the graph is going to move in those intervals. Okay, so we've gathered all the information from the F prime side. We could fill out the bottom and say interval decrease, interval decrease. Oh, and also this interval decrease, we cannot merge together. Okay, so this one you have to separate. You can't say -3 to 0 and just merge that together. There's an asymptote there. So that's why I like to just always separate. Because then I never have to worry about, wait, should I combine or separate? It's just always, if I always separate, then there's never going to be an issue. Okay, so now let's explore what to do with the second derivative, right? So if I want to find the second derivative, what's involved here?
Quotient.
Quotient and chain. And if you ever having to decide which one comes first, look at your parentheses, okay? If your parentheses is over everything, chain rule comes first. If parentheses is only over a portion of the problem, that means there's a larger rule that you want to apply first. You want to apply the rule that affects a larger portion of the problem first. So here, quotient rule has a larger impact than the parentheses, which is only in the denominator. So we start with quotient rule, and then once we get to that G prime portion, then we can apply chain rule for that denominator. Okay, so let me work this through from the beginning here, starting with F prime. Okay, what's F prime going to be here? 56. Keep the 9 minus x squared intact. Back to F. Okay, G prime, this is where chain rule gets activated, right? Okay, outsize derivative. 2 parentheses to the first power, keep the 9 minus x squared inside. Times what? Negative 2x. All over denominator squared. Okay, we do need to clean up the numerator because we need to look for critical points. We could FOIL all this out, combine like terms, but I want to show you something that we can do to save a little bit of time. It still is going to take a little bit here, but I'm going to clean up F double prime just a little bit here. Not much. Let's see, this is negative 4x here. I want to show you that what we can do here, rather than foiling all this out and distributing. We can think of the numerator as, okay, maybe there's a GCF that I can pull from these two messy terms. Okay. So between these two messy expressions, what's common between these two? 36 and 9 minus x squared. And if I can pull that GCF from both, it makes it a little faster to merge the rest. And also kind of moves us closer, faster towards factor form as well. So do you guys see that? I see something shared between these two bracketed regions. So I'm going to pull those out. So I'm going to pull a 9 minus x squared and a 36 from both. So really, I'm dividing this out, right? So if I take this and if I divide this out, what's left over?
X squared.
I have 9 minus x squared still, right? So there's two of them here. I took one of them out. There's still a 9 minus x squared, but it's a lot cleaner. I'm going to just go ahead and put a plus here because the negatives will cancel out. If I take out a 36 and a 9 minus x squared, what's left? The x and the 4x, right? So that becomes plus 4x squared. And that just kind of speeds up the process a little bit into getting it into the factored form that we want to be at. And we still got to do a little bit of cleanup, but it's not bad, right? This we can do quickly. But notice that this is out as part of the factored form. And here's my cleaned up f double prime. Well, a cleaner version of it. Now I say that normally we don't touch the denominator, but in this case, everything is nicely factored. We do see a common expression that we can remove from both top and bottom. But normally we can't do that here, right? That's too soon. But if you don't see any addition subtraction up top, this we can do. Okay, so the whole purpose to get it into this nicely factored form is so that we can look for the candidates for point of inflection and to fill out our second derivative sign line. So remember, we got to look in both the numerator and denominator locations. Do we have anything from the numerator that we can pull? Any critical points if I set the numerator equal to 0? Why not?
Because you can't make the 3x squared negative.
Yeah, so if I set 9 plus 3x squared equal to 0, I'm going to run into an issue. Imaginary numbers, we're just going to be dealing with real number system here. So we get 3x squared equals -9. Can the square root of a negative value? So nothing from here. But the denominator, if I set that equal to 0, I'm going to get what? And -3. Now, do these values have a chance of being a point of inflection? They don't. What's the issue? We already know that they're asymptotes, right? But they keep showing up on our sign lines because they do help separate our intervals of increase, decrease, as well as concavity, concave up, concave down. So we have no candidates for point of inflection, but we can still move forward with our second derivative sign line. Okay, so I'll test -4, I'll test 0, and I'll test 4. Looks like I don't have to worry about the numerator, right? My numerator is always going to be positive. I have to worry about my denominator. So I plug -4 in here. 9 minus 16, that's negative. Negative cubed is still negative. So concave down. 0 into the denominator, I get 9 cubed, which is positive. My numerator is positive, so it's only the denominator I have to worry about. Plug 4 in, 9 minus 16, negative cubed is negative. Okay, so no points of inflection. I do have a couple of intervals of concave up, concave down. Let me see what I can do to sketch the graph. So I have vertical asymptotes at x equals 3 and -3. We know horizontal asymptote is at y equals -2, right? Ratio of the coefficients. We know we have our x-intercept and y-intercept at 0. Okay, I know the middle of my graph is going to exhibit Sorry, I'm pulling this from a different. We know there's a relative minimum at 0, so at 0, 0. So we can kind of just follow the path of the graph here. And then in this region, we want the graph to be decreasing but maintain concave down. Maybe it helps just to find a point in this region so that we can kind of just know where to begin. You also have your calculator as well. So let's say I want to plug in -4. Then I'll get 8 over a -7. So that's going to be a negative value. I know it's going to be somewhere here. That's just enough for me to know that my graph is going to take on this shape, right? The asymptote really kind of helps me shape my graph. I want a decreasing and concave down, so having those boundaries there helps me out. If I plug in 4 here, I get 32 over, this is a negative value, so I know negative value is going to be somewhere here. That's going to be enough for me to sketch my graph. I want the graph to be increasing to the right of 3, but then still maintain that concave down shape. And the asymptotes kind of helps me know that my graph is going to kind of hug along those asymptotes or get closer towards those asymptotes. Sorry? No, I would say everything use parentheses. No, you do U or comma. Just you just have to separate your intervals. Yeah.
Okay.
Okay, so that's just to finish up the curve sketch problem from yesterday. Today, I want to talk about how we can think about a derivative graph and how we can draw a derivative graph. How can we look at a derivative graph and draw the original graph and just kind of go back and forth between them. Okay. So next page, page 36. All right, page 37. And I mislabeled this to be 5.3b here. All right, so let's create a slope sine line for this original function. Okay, so this is the original function. So we can kind of see where the peaks and valleys are. We can see what the slopes are. So I want to create a slope sine line just based off of what we see here. All right, so where do you see relative max? I know it's not quite lined up very well here, but let's treat this like -1. Okay, where do you see slope zeros that we can place onto our slope sine line? Mm-hmm. Mm-hmm. And 1. Now, what is the slope behavior to the left of -3? Positive. Between -3 and -1. Just read the graph as it is, right? Between -1 and 1, positive, and then negative. Now, we are going to create a derivative graph that represents the slope at every point on the curve. So what's different about the derivative graph is that your y-axis represents something else. Right now, your y-axis represents the position of your graph, right? And pretty much what you see is what you get, right? It's up here because it's +4, or it's down here because it's -3. But let's say we had a graph where we're not representing the position of, or the location of the graph anymore. We're now concerned about representing the slope value of this graph. Okay, so I want you to create now an F prime graph. And it's going to feel a little different because your y-axis is going to represent something else. Your y-axis is going to represent the slope value of your original function. The slope value of your original function. So I like to kind of define my regions, so I kind of have a better feel for what I want in my graph. So do we agree that all these are positive y values, but these are all positive what for this problem? Slope values. So I want you to put here, this is where all the positive slopes go. Anything below here, these all represent negative slope of your original function. And anything on the x-axis represents what? Slope zero. Now, I want us to make sure that we understand that your derivative graph is not going to look the same as your original graph, right? So if you're tracing your derivative graph and you realize you're tracing the exact same graph, something is not quite right. Okay. Now, where are the slope zeros from this original graph? The axis. Right. -3, -1, and 1, right? These are places on my original graph where my slope is 0. So if my slope 0 is now going to be on the x-axis, I'm going to have to place these points on the x-axis. So these will kind of act as our anchor points here. Okay, does that make sense so far? Right. Now, everything to the left of -3 is showing a positive slope. So that means everything to the left of -3, where does it have to live? These values have to live above the x-axis. Above the x-axis. But it's going to have to connect to this point, so it has to come down like this. And I'll address that in a moment. It just feels weird, right? It's like, wait, I have a positive slope here. Why is this decreasing? But for now, let's just place them where they're supposed to be, and then I'll address that in a moment. Now, between -3 and -1, what do you notice about the slope? Yeah, it's negative slope, right? And so negative slope on the derivative graph, it needs to live where? Below the x-axis. So it has to start here, it has to be down here, but it has to loop back up because we know it has to connect to that point. So now, if you ask, wait, how far low am I going to go? We're not too concerned about that. Just we know it has to loop back up. All right, between -1 and 1, my slope on the original graph is positive, so that needs to live above the x-axis. So, but you see that point there, it's going to have to be in this region, but has to come back down because I've already established that that's part of my graph here. And then to the right of 1, negative slope below the x-axis. Okay, any questions here? The one question that students have is, wait, it's like this feels weird. Like if I have a positive slope, why is this decreasing? So let me do some ballpark values here. This is obviously not accurate, but just to kind of give you an idea, let's say this is a pretty steep slope of 4, right? What's going to happen to the slope as I get closer towards the top? 3, 2, 1, 0. What's happening to these numbers? They're getting smaller, so that kind of fits over here, right? Slope, this is 4, 3, 2, 1, 0. Instead of representing it as slope form, is now representing it as a y value form. Now, something that I would have to tell you at the beginning here, I want to also connect this with second derivative sign line. So let's say on this graph that there is a point of inflection at -2 and at 0. Okay, I want you to look at the graph here. If these are points of inflection, tell me the concavity here. In this region, this graph is what? Concave down. In this region, the graph is concave up. In this region, the graph is concave down. Okay, so my points of inflections are at -2 and 0. So I'm going to create a second derivative sign line down here. Okay. Okay, I'm basing the shape off of the original graph here. So you said concave down first, right? So concave down. Concave up. And concave down. All right, let's create a second derivative sign line. Now, guess what? The y-axis is now going to change its purpose again. So before, the y-axis represented position. Next up, f prime, the y-axis represents the slope value of the original function. So guess what? Now the y-axis represents the concavity value of the original function. So anything above the x-axis will now represent where my original graph is going to exhibit what? Concave up. So I'll just show that symbol so that we can have an easier time matching up. Anything below the x-axis now represents negative concavity values, which is where my original graph is going to show concave down. Anything on the x-axis will be what? Potential POIs, assuming that it changes signs. So where does the -2 and 0 go? On the x-axis, right? Because these are places where second derivative is 0 or point of inflection. So -2 and 0. Now, to the left of -2, where do I want my graph to live? Below, but it has to connect to this point, right? So I know it has to rise up. Between -2 and 0, I want my graph to live above, right? Match the symbol, but it has to come back down, has to loop back down because of that point there. And then to the right of 0, down, below the x-axis. Okay, I also want to make a connection about these graphs here. Okay, in terms of a function. Let's say this graph is a -x to the 4th power. Okay, let's say this is a degree 4. What's the derivative of -x to the 4th?
-4x cubed.
-4x cubed. Does that match the shape of this graph? Yes, right. Well, I'm just talking about cubic here, right? This is a cubic function, right? My degree is going to drop and my graph is going to show that as well. Okay. What's the derivative of -4x cubed? -12x squared. -12x squared. Look at that power there. That's degree 2. My second derivative also shows that quadratic relationship. I do want to make another connection here is the majority of the problems that you're going to do is from this perspective, where you're starting with the derivative graph and you have to create or answer questions about what the original graph looks like. Or you start with a derivative graph and they're asking information about the concavity or about the point of inflection. Right? So I do want to make some connections here between the first derivative and the second derivative. So if you look, where is -2 and 0 located on the derivative graph?
Oh, when it's so.
Yeah, when slope is 0. So if you're looking at the derivative graph, okay, your x-intercepts will be where your slope of the original graph is 0. Wherever the peaks and valleys are, these are going to be where your point of inflections are going to live for your original graph. Okay. And then wherever my slope is negative, that's going to be corresponding to where my graph is going to be experiencing concave down. Okay. Yes.
Second derivative graph. What are the things you're looking for? Like, what are the things that are?
I'm looking for the shape of the graph, and I'm looking for you hitting the point of inflection, correct?
Okay, so if our peak is a lot higher.
That's fine,
at
yep.
least it just has to be
Exactly.
at zero slope.
Yeah.
Okay.
I want to see the x-intercepts, and it can be higher, it can be lower, but I'm looking for the shape. Yeah, looking for the shape. Okay, so this is a negative slope. So this is where my slope is moving in the negative direction, right? It's not just positive, it's not just negative, but whenever my slope is moving in the negative direction, that's when concave down occurs. That is where we see that relationship, concave down. Wherever my slope of the f prime is becoming more positive, that's going to shape that U pointing up. That's going to represent a concave up. Anytime where my f prime is showing a negative slope, that's going to correspond to where my original graph is going to be concave down. So we can actually pull point of inflection and concave up, concave down simply by looking at the f prime graph. All right. The x-intercepts are your slope zeros. Your x-intercepts could be relative max, relative min. And then your peaks and valleys will be your points of inflection. And then your negative and positive slopes will correspond to your concavity. Okay, I want to try to put it all together for us. We're going to start from this perspective and move forward. So let's skip number 2. Number 2 is also the original function. I want to look at something from an f prime standpoint. So this is the f prime graph. Number 3. So the way that I like to create a bridge so that I can kind of have a visual picture as to what to do, because the tendency is we want to sketch the, if I actually sketch the graph, you may start making it look like this, which is, we know that's not the case, right? You know your function is not going to look like your f prime graph. So I like to go ahead and start labeling what I'm dealing with here. This is not the shape of the original graph, but I can gather some information about what I know to be true about the original graph. I know that anything on the x-axis is where my slope 0 is going to exist on my original graph. Anything above the x-axis is where my original graph is going to exhibit what? Increase, positive slope. Anything below the x-axis is where my graph is going to exhibit a negative slope. So what I like to do here is I like to create a slope sign line, because if I can see a slope sign line with all the arrows are going to be the picture of what my graph is going to look like. It's going to match the rise and fall of what I really want of my original graph. So what can I place onto my slope sign line? Yep, my x-intercepts, right? These are places where my potential relative max and relative min could occur. Now, don't look at the rise and fall of the graph. Look at the location. Where is the f prime graph located to the left of -4? Above or below? Below. So look at what it means negative slope. So put an arrow that represents the true motion of the graph. Okay. I know it's rising, but that's something else. Okay, just look at the fact that it's below the x-axis. Where's the f prime graph located between -4 and -2? Above, right? So match the location between -2 and 1. Below. And to the right of 1. Also below. Okay. This is how you want your graph to look. Okay. I don't really care how high or how low your graph is. If you can sketch your graph and make it shaped like this, that's all I'm looking for. So what do you expect at -4 then of the original graph? Relative min. What do you expect at -2? Relative max. And that 1, and that neither. Okay. So don't look at this graph anymore. Base your graph on those arrows and just let those arrows guide you. Now, you can have your relative min in a different location than me, and that's perfectly fine. I'm looking for your shape. So I like to make things more dramatic, so that's easier for me to sketch my graph. So I think of relative min as a lower point. So I'm just going to kind of pick a relatively low point on my graph. At -2, I want it to be a relative max. So somewhere at -2, sorry, at -2, I'm going to pick a point that is higher up.
We don't have to worry about concavity, but sketching this.
Yeah, let's not worry about concavity. Yeah, so I just want you guys to sketch the original graph. Yeah, right now, let's not worry about concavity. And chances are we're not having to worry about it either. Just if you're going for f prime to f of x, just get the shape of the graph. That's enough. So I want a relative min at -4. So I'm just going to just sketch my graph, make it a relative minimum. I want a relative max at -2, so I'm going to rise up to -2. I want my graph to level off for a moment at 1, but then continue decreasing. So I'm just going to let it flatten out for a moment at +1 and continue decreasing. So if your f of x graph looks like f prime, something is off, right? This should not look like your f prime graph. So if I ask you for increase, decrease, relative max, relative min, just look at your sign line. Your sign line will answer everything for you. Now we can also answer questions about the concavity of the original function. We're not going to look at this. We're going to look at the slope sign line. Okay. All right. Where do I find points of inflection? The peaks and valleys of my f prime. Okay. This is where the maximum or minimum slope of the graph is going to exist. So it's going to be the steepest points of the original graph. So these are going to be your point of inflection of the original graph. Okay. So let's create a second derivative sign line. Place those x values onto your second derivative sign line. So -3, -1, and 1. And now, to pull the concavity of the original, don't look at the shape. Don't think, oh, this is concave down, this is concave up, this is concave down. This is not the original graph, right? The way you pull, yes. Oh, you mean right here?
Yes.
It doesn't matter. Yeah. So any peak or valley of your f prime graph is your point of inflection. Okay. No, yeah. So right now I'm not matching this up with concavity. I just want to get the basic shape. Yeah. Okay. So we're not going to look at the concavity based off of the shape. Okay. Look at your slope. Okay. So here, what do you see here? This is, what slope is this? positive slope. So positive slope of the F prime graph is going to correspond to the what? To concave up, yeah. Of the original graph. Yes,
Just the net. Does it matter? It's if the points are above or below.
That's it,
that
right.
makes sense.
right now, we don't have enough information to plot this, unless I told you, use these points to help anchor.
Okay.
If I give you free form, then it can be above, below, as long as the shape is matching.
So it matters where it is left or right, but not up.
It does matter left and right, yeah.
Yeah,
I
okay.
do need a relative min at -4. I do need a relative max at -2. Yeah. Okay, so between -3 and -1, what do you see? Negative slope. Negative slope means concave down of the original graph. Positive slope means concave up. Negative slope means concave down. Now, based off of this, we can answer all these questions about point of inflection, concave up, concave down. But we can also sketch a second derivative graph based off of these notations. So I want to graph a second derivative graph based off of what I see here. Remember, your second derivative graph represents concavity. Above is concave up, below is concave down. On the x-axis is point of inflection. So we see point of inflection at -3, -1, and 1. So you're going to place them onto your second derivative sign line, second derivative graph, rather. So to the left of -3, where do I want my graph to live? Above or below? Above, but it's got to connect to this point, so it's going to have to kind of decrease here. Between -3 and -1, where do I want my graph to live? Below or above?
Below.
Below, but it's got to loop down and come back up because I already have that point established. Between -1 and 1, above, but it has to come back down. And then to the right of 1, below. This is a very rough estimation of the graph, but this is enough for, if it's a matching problem on the AP exam, this will be enough for you to match. Okay.
Also on the AP exam, there's like, it's just faster with process elimination, right?
Right, exactly. Yeah, yeah. But I want to kind of show you from scratch, and I want us to practice a bit more with this on Monday, but we'll start into optimization. Okay, so check your calendar for your homework assignments. Okay, come get your phones.
Finish the last one.
Okay, great. I will mark it down.
Why is that concave down between -1 and 1? Isn't it below the x-axis? So would that make it? Oh, wait, or is
Yeah,
that?
if it's below the x-axis, it's going to mean a negative slope.
Yeah.
But if you want to interpret concavity off the F prime graph, look at the slope.
Oh, okay.
Because if the slope is rising, that means the graph, the slope is becoming more positive.
Yeah.
When the slope becomes more positive, it's going to create a U shape. And it's going to be
Yeah.
the concave.
Okay, thank you.
That's fine.